Hello, this is an introduction to database design. The design principles I'll talk about apply to relational systems such as MySQL, DB2, Oracle, and SQL Server. I'll talk about them in the context of SQL Server just because that's the relational system I've used the most. My name is Alan Brewer. I've been working with databases for over 30 years. I joined Microsoft 20 years ago, spent 5 years on the SQL Server support team, and 15 years on the SQL Server documentation team. In 2011, at the annual SQL Server Users Group conference, I talked to several senior database administrators who said they're still spending a fair amount of their time having to go in and fix databases that were built by people who didn't understand database design. And the problems with these databases usually with the tables, which are the fundamental units for storing data. And the new people are designing sets of tables that work okay as long as the database is only accessed by 15 or 20 developers and testers. But when you deploy it to production, especially if it has to support a website that's being used by tens or maybe hundreds of thousands of users, the table structures just can't handle the production processing loads. And it's difficult to go in and change table structures. They greatly influence how data is returned to the queries coming out of the application layer. So if you change the structures of your tables, you often have to spin up your dev team to go back and recode and retest the affected parts of their application. And there's a lot of material available about what constitutes efficient database designs. And sometimes the new people are just not finding it, but more often they don't find anything that can teach them the fundamentals of relational concepts and the basics of the design process before they have to start building the database for the project that they're on. And I had that same problem back in the 80s when I was trying to transition from the older hierarchical and network architecture systems to relational systems. But I got into one meeting where one guy got the rest of us to where we understood relational concepts and the normalization design process in about 45 to 60 minutes. And over the years I've taken that approach and built a series of presentations I've given internally at the companies I've worked at that have also been very effective at getting people to where they understand the basics of the database design process. So now I'm publishing it to the web where it can hopefully be a resource for other people who need to quickly understand how to do good database design. So if you don't know anything about database design, at the end of this presentation you should be able to build better databases than you would if you just winged it with what you know now. But the most important part is that you should have enough of an understanding of the core relational concepts and the normalization design process that now you can go back and more easily understand the more extensive material available on the web and in books. And it's important to understand you need to do that because in an hour I can only give you enough information to give you the equivalent of a learner's permit. You won't make some of the fundamental design mistakes, but you'll still make some others because of other factors that impact good database design. And there are a lot of other things that we just don't get time to cover in the course of a 1-hour presentation. So if you're going to design more databases in the future, you need to make a commitment to going out and reading the other material that's available in books and on the web. A relational database gets its name because the basic unit for storing data is a thing called a relation. And on the surface they look very simple. They look like a two-dimensional array or a table with rows and columns. But there are a lot of rules about how you need to structure your relations so that they're as efficient as they can be at storing data. And there are other rules that operations on those tables need to comply with to maintain that efficiency in storing data. And those rules were originally defined back in the 1800s by the mathematicians who were coming up with set theory. They realized there were certain classes of sets that had this two-dimensional array type format that were very efficient or could be very efficient at storing data. And they came up with mathematical proofs for the sets of rules that you needed to follow to get a set of relations that would be highly efficient at storing data. And in the 1960s, a researcher at IBM, Dr. E.F. Codd, was trying to decide what's the most efficient way to structure the data in a central database where multiple applications can work on it at the same time. And he started realizing the characteristics that he was defining for that system were very similar to the characteristics that the set theorist had defined for relations. So in the late 60s and early 70s, he published some papers that applied relational theory to the storage of data in a central location. And nowadays, the types of relational systems that are most available commercially are all SQL systems, and they're named because the data language that applications use to work with the data is the structured query language, or SQL. And that was originally defined by the first teams at IBM that took Dr. Codd's ideas and actually started implementing relational systems. And IBM took the SQL language to the international standards bodies, and it became an ISO standard for SQL and an ANSI standard for SQL. And so most relational systems now use that as their data language. And in an SQL system, we tend to not use relational terminology. For example, we talk about tables instead of relations. But everything in an SQL system still needs to comply with those rules established by the set theorists back in the 1800s to maintain the efficiency at the tables or relations for storing data. And you have to design the tables to follow some of these rules for those tables to be able to support all the efficiency they can. And in his original papers, Dr. Codd defined a design process called normalization that he was able to mathematically prove led to a highly efficient set of relations that minimized data redundancy, so that you ended up that you didn't have multiple copies of the same piece of data in different places. You ended up with one copy of the data in one column, in one row, in one table. And that's important because if you've got multiple copies of your data around the system, you have the possibility of introducing anomalies in your data maintenance operations like insert, updates, and deletes. If you only remember to perform that operation on some of the pieces of data and not others, you've now got an anomaly or an inconsistency in the state of the different pieces of your data. So for example, if you've got personnel information in 5 different places in your system, and one of your coworkers gets married, closes her checking account, and opens a new checking account with her husband and changes her name, and you remember to update that in 4 places, but you forget to update it in the payroll system, she won't be very happy on payday because your company will be trying to deposit her paycheck into a checking account that no longer exists using a name that's no longer valid. And over the years, I realized that a lot of database designers used another process called entity relationship modeling, or they used tools like Irwin that were based on entity relationship modeling. And they got a very similar set of tables that you got if you applied the normalization process. And a few years ago, the man who originally defined entity relationship modeling gave a presentation here at Microsoft, and he said he started from a slightly different perspective in relational theory, but his process was also mathematically proven to lead to a very efficient set of tables for storing data. So 2 different design paths that get you to the same goal. In this presentation, I'll talk primarily about normalization because a lot of the database books use the normalization terminology. And if you understand the core relational systems and normalization, then it's usually relatively easy for you to go pick up an understanding of entity relationship modeling. So in an SQL database, your main unit for storing data are tables, and when you go through normalization and ER modeling, you end up with 2 broad classes of tables. The first class of tables you get are entity tables, and they just represent the things for which you need to store systems or store data. And an example would be if I'm doing an education system, then I'd end up with entity tables for things like students and courses and classrooms and teachers. A couple of things about entities. Number one is that it's sometimes a point of contention within the design team that different patterns of entities can be designed for the same system, and they're all fairly efficient at storing data. So at the end of the day, you just have to pick one and go with that pattern and implement that pattern. The other thing about entities is don't assume they have to be something physical, a person, place, or thing. They can be logical entities. So if you're doing business databases, a lot of times you'll end up with entity tables for logical events like placing an order or making a payment or tracing some event in a manufacturing process. The other type of table you end up with are relationship tables, and they simply establish the relationships between entities. So if I've got an order entry subsystem and I've got an order table and I've got a product table, in between I'll have an order product table, which is where I specify which specific products were requested on each individual order. Tables have two dimensions. The vertical dimension is called a column. It's called an attribute in relational theory. And the columns represent just some characteristic of whatever it is you're modeling with that table. So if I have a product table, I would expect columns for characteristics such as the product number, the name, the color, the weight, and the price. And when you think of columns in the design process, you're trying to define two elements. One is the data type, so it's just what format of data can I enter in this column. So for something like a name column, I would expect to choose a character string data type. A weight column, I would expect to choose some kind of numeric data type. The other thing that you're trying to determine at that point are the domains for each of the columns. And the idea of a domain is that out of all the values I could possibly specify given the data type format for a column, only some of those values will really have meaning for use in this column. So the domain are the set of values that will have meaning for use in this column. Sometimes we talk about them being the set of allowed values in that column. So a good example is a color column. It's a character string, but if I try and enter strings like tree or run or Washington, they don't really have any meaning for use in that column. What you need to specify in that column are character strings that represent the name of a color like red or white or blue or green or yellow. The row is the horizontal dimension in the table. They're called tuples in relational theory, and they simply represent an individual of whatever's being represented by that table. So if I have a part table, I'd expect one row for part 123, another row for part 124, a third row for part 125. The other key element that you're trying to design or factor in during the design process are the keys. And you start out trying to identify candidate keys. And a candidate key is simply a column or a group of columns whose values are going to be unique for every row in that table. So if I have a part table and I've got a part number column and I've got a business rule that I can only assign a part number to one product, I can't assign it to multiple products, then that becomes a candidate key column. I might have another business rule that no two parts can have the same combination of part name and color and weight, so that could be a composite or multi-column candidate key. The other thing you're trying to determine is whether other columns in the table depend on that key. So if I go to a database and I say retrieve the part row that relates to part number 123, that key value then determines the values that show up in all the other columns. They should be only the values that relate to that specific part. If I want to see values for another part, I need to come into the database and say, show me the row for that other part. So those other columns are said to depend on that key column. And if you've got a large table with a lot of columns, you may have several candidate keys. And out of those candidate keys, you want to pick one that's going to become the primary key or the primary identifier for that table. And this is an area where I really recommend that you do further reading in the books and the web material, because there are a lot of things to consider when picking primary keys. But they need to have some characteristics. Number one, all the columns in the table should depend on that primary key. Another thing is the primary key values should be relatively small. They are the things that you're going to copy out into all your relationship tables to establish your relationships between entities. So you may end up making hundreds or thousands of copies of a given primary key value out in all your relationship tables. So the smaller they are, the less data the database has to wade through to find the right answer. So it can get to be a performance issue. The other thing you want is those key values to be relatively stable. You don't want to have to be constantly updating your primary key values. And the way that you get to having a stable value is you pick a column that doesn't have any inherent meaning as a characteristic of that particular product. So for example, if I've got my part table, part number would be a good candidate key, or a good primary key. It's relatively short, and part numbers really have no inherent meaning within the value of a part number key. If I pick the other candidate key of the combination of part name and color name and weight, now I've got problems, because part name and color name actually have some inherent meaning. And if I'm trying to build a database for some company that's in the fashion industry, those names can change every year because the marketing guys will come in and they say the product names and the color names that we chose last year really resonated with people looking for last year's fashions, but they're not very exciting for people looking for this year's fashions, so we need to change them to names that resonate with people looking for this year's fashions. So you want to keep it fairly small. Sometimes when you look at the candidate key columns that occur naturally as your process of building out all the business requirements for the data and coming up with columns that satisfy all those business requirements, sometimes in those naturally occurring columns you don't find a candidate key that would make a good primary key. And at that point you start thinking about internally generating another primary key column where you internally generate say integer numbers or something to use as a primary key. And there are a lot of other considerations you need to factor in before you make that decision. So if you start thinking that you need to do that, go look at some database design books and understand all of the different factors you need to consider before you make that decision. The other kind of key you have are foreign keys, and they are the things that establish relationships between tables. None of the SQL systems I've worked with have any kind of physical linkage between tables. What happens is that you have a foreign key column in one table that has the same domain as a primary key in another table. And if I find rows in the first table for which I need information out of that other table, what I'll do is I'll take those foreign key values and then do a join to the second table on its primary key to find the rows that have that additional information that relate back to the rows that I've had in my table. So an example would be if I've got an order table that has order ID as its primary key, and then I've got an order products table that has a compound primary key that is an order ID column plus a product ID column. If I find rows in the order product table that are interesting to me and I want to see who ordered them, when the order was placed, where they got shipped to, then I'll take the order ID values for those rows in the order products table and do a join back to the order table and look for the rows that have the same values in the order ID primary key over there so I can get that information about those orders. This is just a simple visualization of how you can conceive a table looking. This is a simple part table. It's got 5 columns. It's got a part number, name, color, weight, and cost column. I've chosen part number as my primary key, which is why it's shaded a slightly darker color, and it meets those requirements of being relatively small, not having inherent meaning, but all these other columns depend on it. When you go in and design a set of tables in your database, you follow an overall process that's similar to how you design things for any computer-based system. First, you go out and interview your end users and establish all the requirements. Then you come back in and you define a logical model, and in this case the logical model just represents the structures of the tables that you want to build. You're not taking into consideration anything you have to do that's specific to the database you're using for this project. The logical model could be implemented on any relational system. And then once you've verified that back with your users and got sign-off that your logical model will support all the requirements, then you'll build the physical model, and that's where you come up with the specific scripts and SQL statements needed to create the tables on the database that's being used for this system. And some things to think about when you're up in that first phase, if you actually go out and interview end users, at the same time the application designer is probably interviewing the same user. So you guys need to work together to go out and maybe interview them at the same time so that you don't annoy them by the two of you asking the same questions at the same time. The other thing is that the application designers and the application developers, you should consider them as your users, because there may be some data requirements that come from the internal processing of the application that none of the actual business end users understand. And so you have to interview the application designer and the developer to understand what those internal requirements should be. Another thing is that you might get into some contention with the application developers, because developers working on some specific web pages or forms or reports are going to want to see table structures that are very close to those forms or reports so that they have easy transformation of the data from the tables into whatever form or report that they're building. You, on the other hand, you need to design a set of tables that are going to be highly efficient at storing all the data needed by all the processes that the application has to support. And sometimes that's going to lead to table structures that don't really look like what's being presented back in the forms and the reports. And so you really need to stick up for the database design that's going to be highly efficient for meeting the processing needs of the application, and work with the developers so that they understand the kinds of SQL queries they need to build to take the data that's in the table structures you have and transform it into the format that they need to present it in forms and reports and web pages. Step number 2 is the critical step. If you don't come up with a good logical design, there's nothing you can do later in the physical design or after you've rolled the database into production to deal with big problems in your logical design. And this is where it's crucial to do a systematic design process like normalization or ER modeling to ensure that when you come up with your set of tables, definitions in the logical model, that you have the right set of tables and that they're going to be highly efficient at storing data. When you get down to the physical model, that's where you can start taking advantage perhaps of extensions to SQL that's offered by whatever database you're using for this project. And at that point you really need to be thinking about, I've taken this excellent logical model, I'm now just going to go through a relatively straightforward step of creating the create statements that will create that set of tables. From this description, don't assume that database design is something that happens once in a development cycle. In today's world of iterative development, it doesn't work that way. What is going to happen is that some early sprint in the dev cycle, you're going to come in and you're going to do your initial database design at a point where you understand the fundamental data requirements for the application as a whole, and you know for sure the database parts that you have to come up with to support whatever functionality is being developed in that particular sprint. And it's really critical to do normalization or ER modeling at that point, because you want that first part of the database to be rock solid. You want it to be the foundation that you can just add things into for later sprints, because you just want to go to a later sprint and say, what's the new functionality you guys are doing? And for any data requirements, you want to just be at a point where all you're having to do is maybe add columns or maybe add tables to your existing database design. You're not having to go back and massively restructure the tables that you've already done. So if you do normalization or ER modeling for each step, your chances of having to do a massive reorg are greatly reduced. And the thing you really don't want to have happen is if you get to a sprint like 10 or 11 and you have to go back to the management chain and say, you know, I just did a bad job of designing that original database. I've got to go redo the whole database because everything's fallen apart, and you guys are going to have to burn a whole sprint where you're just recoding the application to work with the new table structures. You're not going to be able to do any new feature work in that particular sprint. And normalization and ER modeling are the kinds of things that can minimize the chance of that happening. Normalization gets its name because you start with a set of tables, they're prototypes called data views, and then you apply a series of rules that lead those structures to be more and more efficient at storing data. And each of those rules is called a normal form. And each normal form assumes that you've already applied the rules for all previous normal forms. So you start out with first normal form and apply its rules, then you apply second normal form rules, and then third normal form rules. And in his original work, Dr. Codd defined the first, second, and third normal forms. A little while later, he and Edgar Boyce, who was one of the designers of one of the original relational systems at IBM, redefined the second and third normal forms into the Boyce-Codd normal form. So you can either do first, second, and third normal form, or first normal form, then Boyce-Codd normal form, and you get to pretty much the same point. And then after that, you start doing like fourth normal form, fifth normal form, and there's something like 20 normal forms. And in the old days, most database developers said, you know, if you've got to third normal form, you've pretty much taken care of any of the major issues in your database, and you're good to go. And sometimes you'll still run into database developers that say, I've been designing databases for 15 years and I've never had to go past third normal form. But fourth and fifth normal form deal with complex relationships, and as databases get larger and more complex, there's more of a likelihood that you might get impacted by the issues that fourth and fifth normal form are designed to meet. So it's a good idea to go read the books and get more information about fourth and fifth normal form and evaluate your database against those normal forms too. So back in the days when third normal form or Boyce Codd were the design goals, somebody came up with this cute little phrase that by the time you get to third normal form, all the values in a row should depend on the key, the whole key, and nothing but the key. This is a one-page summary of the normal forms and the rules you apply to go from one normal form to the next. And then on the next page we'll start an exercise where you'll actually see these rules in action. So you start out by building a set of data views. And data views are like prototype tables. They have the same structure. They're essentially a set of columns. And at this stage, the thing you're really focused in on are, do I have all the columns I need to store all the data that the users have identified to me as business requirements for this database? And for those columns, you want to go in and start doing your definition of what's the right domain to enforce the business rules for this particular column, and which of these columns seem to be candidate keys that they have other columns depending on them. And you'll see in our exercise that you can start with a really bad one-table design, and you can somewhat rely on the normalization process to pull that apart into a reasonable set of entity and relationship tables. But experienced database designers, they've seen this pattern evolve before, and they don't start with a bad design and rely on normalization to pull it apart. They usually start with a set of entity and relationship tables, and then they use normalization rules more as a double check to make sure that they haven't cut any corners or missed a step when they were designing their process. So once you get your data views put together, you apply a couple of rules to get them to first normal form. And the first rule is that you want all the columns to be reasonably atomic, or atomic enough to support your business requirements. So you want each column to be a single unit of information. You don't want columns to have subparts. So for example, if I've got a name column, that's not a good solution, because in the name I can have a name prefix like Mr. and Mrs. I have first name, middle name, last name. And database engines are actually engineered on the assumption that your columns are atomic units of meaning. And they don't have syntax that you can say something like, okay, in this name column, sometimes a middle name will be the third node, sometimes it will be the second node, sometimes it won't be there, but go ahead and create an index on that anyway. And so if you need to apply indexes to the separate nodes, or you've got business processing for the separate nodes, you don't want to keep trying to have to implement application logic to pull those pieces out of the individual nodes. And so you really need to split that out into multiple columns. And this is another area where you sometimes get into some heated discussions about what is the right level of atomic characteristics to get to. Because if you talk to somebody who's a computer scientist, they'll say, well, you know, a character string is just an array of characters, and if you're telling me I have to get to atomic units, those atomic units are each individual character. So you're trying to tell me I need a column for every character in my table, and that just doesn't work. And what you really need to use as your guiding light is, do I make any business use, or do I have to apply any performance optimizations to any of the subnodes within this column? If not, you may elect to leave it together. For example, if you're doing phone numbers for a U.S. company, U.S. phone numbers have a 3-digit area code, a 3-digit exchange within the area code, and then a 4-digit phone number within the exchange. And you may elect, if your business processing doesn't ever do anything, you never apply any analytics to try and determine what customers and what exchanges buy what products, then you may elect to leave it in there if all you're ever going to do is use it to call back to your customer. But if you make that decision, there should probably be a little warning bell going off in the back of your head that all it takes is one new business requirement coming in that is going to make you say, well, now I really do need to split that apart into more atomic units. The other thing that you're looking for at this time is if you've got any sets of columns that repeat multiple times, or if you've got keys that repeat multiple times, and we'll see an example of that in our exercise. And you want to move those repeating groups of columns out into a separate table. So once you have applied those two rules, you've got to first normal form, you'll be in a state where all your columns depend on a key and all the columns are atomic, And then you apply the rule to get to second normal form, which is you want to remove partial key dependencies. And the example we'll see is we'll have a table that has an order ID primary key combined with a part number primary key, but some of the columns are only going to depend on part number. They have no dependency really on order ID. So we want to pull those apart to create a separate part table. And once you've applied that, you should be at a second normal form where all the columns depend on a whole key. And then the rule you apply to get the third normal form is you remove any non-key dependencies. And the example we'll see is we'll have an order table that has a lot of customer columns in it that relate to a customer number, but they really have no dependency on an order ID key, so we need to move those apart out and create a separate customer table. And once you've got to third normal form, you're at a state where all the columns depend only on the primary key, the whole primary key, and nothing but the primary key. And then fourth normal form, you want to get to a state where you don't have tables that are trying to represent multiple independent multi-valued facts, because those can lead to an explosion in data redundancy. And I've added a slide to this deck to show you the basic pattern that you're trying to fix with fourth normal form, and we'll talk about that after the exercise. So this is our exercise. This is actually an interview question I've used for the last 25 years or so for a support engineer candidate or a writer candidate. I would give them this form and I would ask them, if you normalize the information on this form, what would be the set of tables you would expect to see? So the first thing you do is you start building out your data views, and you list the data views, you make sure you've got all your columns, and for all the columns you go in and determine what the domain should be for that column, what business rules apply to that column, and you then start determining the candidate keys and start understanding which columns have dependencies on other columns, and then you want to bracket or somehow identify any repeating groups that you've got in your data views. So for that one form, I did the rookie mistake of saying I got one form, that's one table, so I have this order table. And in here I've started thinking about what are the columns, and for each column what is its name. I'm taking a first guess at the data type I'll assign, and these are SQL Server data types. I start thinking about what's the domain, what are the business rules for this column, and is this column a key? And then down in the part columns, the number, description, color, those are the things that are representing that box in the middle of the form where you could specify up to 6 different parts on each order. So these would actually need to be a repeating set of 6 of these columns, so it's bolded to represent that it's a repeating group. And when you start thinking about things like domains, you have to start thinking about things like the order date column, which is the second from the top. I've assigned a domain that says business date because in my interviews I've found that the store is only open on Monday through Friday. It's closed on holidays. Therefore, it's not valid for somebody to be able to place an order on Saturday or Sunday or on a holiday. So I need a domain that says I can enter those kinds of dates into this column. And then delivery date, I found that the store, all they do is hand the packages off to UPS or FedEx, and they deliver anytime, so it's valid to have any day of the week or even holidays represented for a delivery date. So we start looking at this in terms of the rules for first normal form, and the first problem we've got is that part is a repeating group, so we need to pull that apart into separate columns. And then name and address and phone number have these problems that there are groups within, there are nodes within those values. They're not atomic columns. And so the rules to get to first normal form are, first of all, any of those columns that are not atomic and have subnodes that we need to work with as part of our business rules, we need to separate those into separate columns. And then we also need to remove the repeating groups. And what we do is we place the repeating groups in a new table, and the key of the new table is whichever column that group of columns had a dependency on, in this case part number, but then you also include the primary key from the source table, and it's going to operate as a foreign key to establish a relationship between these two tables. So let's look at how this plays out. So you can see over on the right we've moved all those part columns out and created an order parts table, and we've put an order number column as one of the 2 columns in the key for this new table, and it's also a foreign key back to order number back in the order table. And back in the order table, you can see the italicized column names where we took name and I just quickly split it out to first name, last name. You would typically split it out to a name prefix and a middle name also. And then on the address, I made some simplifying assumptions that I'm only operating in a city, I'm shipping things that are too big to fit into a post office box, therefore the only address format I have to worry about is one where I get a street number, a street name, and then an apartment or office number. So I've split the address columns out like that. And then I've made a simplifying assumption on the phone number that we're never going to do any analytics on it. The only use we're going to make of it is to call back to the customer. So for the business rules as I understand them now, it's okay to leave it as one column. So now you need to apply the rules to get to second normal form, and you need to remove partial key dependencies. And you've got that problem over in the order part table. The part description, color, weight, and cost columns, they only depend on part number. They don't really depend on order number. And if that means that if I leave those columns in the order part table, that means I have to duplicate those values for every order that references the part. So I'm going to start increasing my data redundancy problems and make it harder for the database engine to wade through all the data to find the right answers. So I really need to pull those over into another table. And so the rule that you apply is that you take those columns out and you place them in a new table, and whichever column that they were depending upon, that becomes a primary key column in the new table. And so this is what you end up with. We now have the order part table limited to just those columns that relate specifically to the relationship between a part and an order. That's all that's left up there in the order part table. All the things that are generic to the part and don't change for each order that references it is now down in the part table. So for each part, I'm only going to have to record its key characteristics in one row. And I've got part number as the primary key down in the part table, but I left it in the composite primary key up in the order part table to establish the relationship between these two tables. And this is now your typical structure of a relationship table between two entity tables. The order table and the part table are entity tables, and order parts is a relationship table, and what you typically see there is it will have a composite primary key that's made up of the primary keys for the two entity tables. So in this case, I've got a composite primary key for order number and part number, and each of those is a foreign key pointing back to the entity table this relationship table works with. So order number is a foreign key back to order number in the order table, and the part number in the order part table is a foreign key down to part number in the part table. So now that we're in second normal form, we need to think about what do we do to get to third normal form. And the problem that we've got here is we're not supposed to have any columns that depend on a column that's not in the key for the table. And we've got that problem of a non-key dependency over in the order table, where all those customer columns, the name and the address and the phone columns, they don't really have any dependency on order number. They only have a dependency on customer number. And again, if we leave them in this order table, then we have to repeat that customer information every time the customer makes a new order. And so we need to apply the rules to get to third normal form that we're going to pull all those columns out into a new table, but that customer number key column we're going to leave as a foreign key in the order table to establish a relationship between orders and customers. And so you end up with the structure that we now have over on the left, where the order table is now much smaller and the customer table has now been created. It's essentially an entity table now for the customers, and we left a customer number column back up in the order table that is now a foreign key down to customer to establish that relationship. So we now complied with all the rules for third normal form, and you can see how the rules for the second and third normal form pulled apart that one table into what's now a reasonable set of entity and relationship tables for the data that was on that order form. When an experienced designer looks at these tables, you're at the point now where you're trying to evaluate whether these tables meet all the business requirements that you know of for this data. And you get kind of nervous about a couple of things related especially to the customer table. One is that the structure of this relationship, where I just have a foreign key from the order table to the customer table, works as long as I only have one customer related to any given order. If I ever get another business requirement that drives more complexity into that kind of relationship, I may need to establish an order-customer relationship table between the two. You also get kind of nervous about the address and the phone number columns actually being in the customer table. From the order form, it looked like a customer only has one address and one phone number, but that's not usual. For example, on Amazon.com, my account has multiple addresses. I've got my home address as my billing address. It's also my default shipping address. But then I have addresses for several friends and family members, because sometimes I'll order a gift from Amazon and have Amazon ship directly to them. So most customers have multiple addresses. You also often have multiple customers sharing the same address. If you've got a husband and wife, they've got the same address even if they have separate accounts. You have the same problem with phone number. Most people have a business phone, a smartphone, maybe a couple of smartphone phone numbers, and maybe still a landline home phone number. And also anybody that lives in the same house will have the same address and the same phone number. So it's much more common to see the addresses and the phone numbers pulled out as separate entity tables, and then something like a customer address relationship table and a customer phone number relationship table. The other reason you have to start thinking about doing that is that you're probably going to identify other entities like business offices and warehouses and retail stores that also have phone numbers and addresses. So address is going to be some entity that actually relates out to multiple different kinds of entities. Another problem you're going to have to deal with, especially if you start doing sales outside of a narrow geographic region, is you're going to start running into phone numbers that have different formats and addresses that have different formats. If you start delivering throughout the United States, you've got to deal with post office box formats, street address formats, rural route formats. If you start delivering to multiple countries, now you've got a lot of different address formats, and you don't have just a zip code. You now have postal codes, and they all have different formats in different countries. Same thing with phones. Phone numbers have different formats for different countries. And so you've got to start thinking about those kinds of things and realize that some future business requirements may cause you to pull those things out into separate tables. Another thing to talk about is the idea of storing a calculated value. So in the order part table, we've stored the order part cost, which is easily calculated by just multiplying the order part quantity times the part cost column down in the part table. And in the old days, when disk space was astronomically expensive compared to today, you tended to not want to store values you could easily compute in the database. It was cheaper to just calculate them whenever you needed to refer to the data. But if you don't store calculated values like that, you may drive other requirements for your database. So for example, if I've got a requirement to be able to audit my orders 4 and 5 years in the future, I've got a problem that part prices don't stay constant. So if I'm not storing my calculation of the order part cost, it may drive another requirement that now I need a part price history table to be able to recalculate those values 4 and 5 years in the future. I've got the same problem over in the order table. The tax column is just multiplying the subtotal times a tax rate, but again, tax rates don't stay constant. So if I need to reconstitute that value for an audit 4 and 5 years in the future, I may need to create a tax rate history table. The other thing that you're doing after you've normalized a form is you go and you start normalizing all of the forms and reports and web pages and trying to come up with things that meet all the data requirements that your database is going to have to support. And as you go out and normalize these other forms and reports, you're going to start getting a lot of the tables that have the same primary key as tables that you've already generated. And so in your final design, you need to merge all those tables together. So for example, we normalized an order form. We got a part table with part number as a primary key. If I go normalize an inventory warehouse form, I'm likely to also get a part table with part number as its key, and I need to merge those two tables in the final database design, because you want to get to the point where there's only one table that records the information that any part of your system needs to know about the parts that your company is selling. And as you go through and do those things, you're constantly wanting to go back and validate your table structures against all of the business processing requirements that the system has to support. So let's just quickly look at how the data actually goes into the table. So I've taken a form, I filled it out. We assume this is the first order form that we've entered in for the system. And when you click submit, these are the rows you're going to have in the tables. You're going to have one row in the order table that records the information specific to that order. That referenced one customer, so we end up with one row in the customer table. If that same customer now comes in and places a second order, we'll get a new row in the order table, but we won't get a new row in the customer table because we've already recorded the information for that customer. And this particular order referenced 4 parts. So we end up now with 4 rows each in the part table and the order part table. But they're recording fundamentally different information. The part table has information that's generic to that part regardless of how many orders it's referenced on. The order part table is the information that's specific to the relationship between this part and a specific order. So again, if I come in with a new order that references the same 4 parts, I'm not going to be inserting any new information in the part table because I've already recorded the information for those parts, but I will be adding new rows to the order part table to show that those parts now have a relationship to a new order. And that is a typical kind of pattern that you start seeing, is that your entity tables tend to have relatively few numbers of rows, and your relationship tables have relatively large numbers of rows. So once you've got to the third normal form, we'll talk quickly about fourth normal form. And the rule for fourth normal form is that the tables should all be in third normal form, and you want to go in and make sure that none of your tables contain multiple independent multi-valued facts about an entity. And you start seeing that potentially in some of the relationship tables. And so if I've got an education system, a class is simply an agreement that a group of students will show up at a specific room at a specific time, and an instructor will also show up and will start guiding the students through the curriculum for a particular course. So it's really just a relationship between a course, students, time period, a classroom, and an instructor. And so you might think, well, okay, it's one thing, it's one set of relationships, so let me model that as one relationship table. And this starts having a problem because these facts are not really that dependent upon each other. And if you start having multiple values for some of these facts, you start exploding your data redundancy. And so if I've got 25 students that sign up for a class, I need to have 25 rows in this table. But when I was in university, classes had 2 typical patterns. They were either an hour on Monday, Wednesday, Friday, or they were an hour and a half on Tuesday, Thursday. So if this is a Monday, Wednesday, Friday class, I now have to represent those 3 periods. But I need to apply each of those 3 periods against my 25 different students. And so now, even though there's not that direct relationship between them or a dependency between them, now I have to take my 25 rows and represent that for the combination of the 3 new values. So now I explode out to 75 rows. And sometimes in university, like my introductory chemistry physics class, it had 2 professors. It had a chemistry professor and a physics professor. So now if I've got 2 instructors assigned to the same class and I've got 3 periods and 25 students, I blow out from 25 to 75 to now 150 rows just to record that data, and I'm duplicating my student information and my period information and my instructor information like crazy. And I'm just creating a big chunk of data that makes it harder for the database engine to wade through to find the right answer for given queries. And the kind of structure that works much better, since these things don't have strong dependencies on each other, is to represent them as individual relations. So the better pattern is that your class table becomes a lot more like an entity type table, and then for each one of these fairly independent dimensions, you have a relationship table. And so my class student table, I just do the 25 rows in there and I'm done, regardless of how many periods and how many instructors this class has. for the class period table, I just put in my 3 rows there. I don't have to duplicate out my 25 rows to create 75 rows. Same thing with the instructor table. If I got 2 professors, it's just 2 rows in there. So instead of having to have 150 rows of data to represent the stuff that's important for this particular class, I end up representing the same information with only 30 or 35 rows. And so it's a much more efficient structure. But this is another area where I strongly recommend that you pick up a database design book or find a web part that dives into fourth normal form in more detail, and also find something that talks about the fifth normal form and its requirements. So once you've done your logical design, you implement your physical model or your physical design. And the main thing I want to say at this point is to address the most common mistake I see new people making at this particular time, and that's that they use some relatively simplistic rule to assign indexes, and especially clustered indexes. They'll say something like, primary key, that's a really important identifier, so I'll just by default assign my clustered index to my primary key. Unfortunately, there have been Microsoft products that made that same bad assumption. And so indexes are access speed mechanisms for the database, that it can more quickly find individual rows. And what you really want to do for your indexes is find out what's the pattern where the where clauses and all the SQL statements coming out of the application reference the columns in this table. So a clustered index is the fastest access method on a table. A non-clustered index is the next fastest. And then if you got a table with no indexes, the database has to scan the table all the time, and that gets to be a performance hog. And what you really want to do is apply your clustered index on whichever column or set of columns is most frequently referenced in the where clauses of all the SQL statements coming out of your application. So if you do an analysis and you find out that 75% of the time an SQL statement references this table, it's got a where clause that says something like where part name equals a specific value, then you want to put your clustered index on part name, and you want to put non-clustered indexes on any other columns that are usually referenced in the where clauses. Where you might need to put the clustered index on your primary key is if you find out that almost all the SQL statements referencing a table are doing it by doing a join from some adjoining relationship table where they're joining in on the primary key. Yeah, at that point it's probably the right answer to put the clustered index on the primary key. But a lot of times it's really not the right answer. And it's sometimes hard to figure out what are all the where clauses of all the SQL statements coming out of my application layer. And so most of the databases have a tool, like SQL Server has a database tuning advisor, where you can do a representative trace of the SQL coming out of your application and run that trace into the tuning advisor. It'll analyze those statements against the tables and give you a recommendation on the set of indexes to apply to those tables. So it's much better to do that than try and assign indexes based on simplistic rules. So now you understand the fundamentals of the structures in a relational set of tables, and the fundamentals of the normalization design process, and you need to keep learning more. And one thing you need to do is keep practicing, because actually having to come up with table designs in a practical sense is where you really start thinking through and understanding the normalization rules. And don't just wait for the next project to come in where you're going to be the database designer. Just go out and pick some form or some report or some web page and come up with a set of tables where you've normalized the information that you'd have to store for that web page or form or report. You really need to go out and pick up some good books on either database design or data modeling. And some examples here, there's a guy named Lewis Davidson who's written a really good set of books I like on how to design databases for the different releases of SQL Server. This is his latest book for SQL Server 2008. He's got a pre-publication notice on Amazon that he's updating this to work with the next release of SQL Server, which is SQL Server 2012. The other thing is, if you're working with another database system or you just want a general database design book, what I've done here is I just went to Amazon, I searched on database design, I ordered by average user rating, and you just pick a database design book that's got an average of 4 or 5 stars and is relatively recent. The other thing to search on would be data modeling. That's a very closely allied field. Another thing is you need to learn as much as you can about SQL. Sometimes because you're going to be the person who knows the most about databases, so you need to be able to help your developers build efficient SQL queries, or you need to you'll find sometimes that performance problems in the database are because of poorly formatted queries coming from the application layer. But you also are going to be using SQL to go out and build your databases, deploy your databases, and maintain the databases and monitor performance. So the more you know about SQL, the better you'll understand how to design a good database to meet the requirements, the SQL statements from your application. It's also a good idea to learn as much as you can about the internals and the specific behaviors of whatever database system you're going to implement your database on. And in the case of SQL Server, there's this excellent series of books called Inside SQL Server 2008, where the users have used SQL Server for 15 or 20 years or more. They also have had chances to come in and interview people in the dev team. So it's just this amazing wealth of information about how SQL Server works. And there's some excellent websites out there that you need to start finding for whatever database system you work with. In the case of SQL Server, there are places like SQLpedia.com and SQLServerCentral.com. SQLServerCentral.com has a huge number of really good blog articles about SQL Server, and they've got a set of forums where you can ask questions of other customers. And that's the other thing you need to really focus in on, is finding out where the community of users of your database are asking each other questions out on the web. Start finding out the set of forums that they're using. In this particular case, Microsoft has a set of something like 40 or 50 forums on MSDN and TechNet that are related to different aspects of using SQL Server and its OLTP and BI tools. And we've actually got a forum that's specific to asking questions about how to design databases for SQL Server, and that's the link I've got here. As I mentioned, SQL Server Central has another set of forums. And when you get into those forums, start identifying people who are giving a lot of high-value answers. In the case of SQL Server, if you see somebody who's marked as a SQL Server MVP, Microsoft has determined that they're doing a lot to support the community with high-value presentations or books or blog articles or answers in forums. And so once you start identifying them, then you go out and start doing things like friend them in Facebook or follow them on Twitter and see who they're following on Twitter and start following those other people. When I first went into Twitter, I just went out and I picked 10 or 12 SQL MVPs and a couple of people from the dev team, and I just saw who they were following, and within 2 or 3 hours I'd built out a list of 7 or 80 people I was following for information on Twitter about SQL Server. One thing about when you go into forums and start asking questions, make sure that you use database terminology. In particular, talk about databases and tables and columns and rows. Don't talk about files and records and fields, because that's kind of a red flag to all the other people that you don't understand even core fundamentals about database design. And unfortunately, some guys that have been dealing with databases for 20 and 25 years have seen so many people like that come in that sometimes they'll snap and they'll flame you for not understanding fundamentals. And the important thing is that don't let them stop you. You've got to keep asking questions, but try and do things where you understand at least the basic terminology so that you can sort of elevate yourself from looking like a total newbie to somebody who's at least gone out and done some basic research. So, you know the basics of designing. Go out, do a lot of practice, pick up some of these additional resources, and go out and learn as much as you can and design the best databases you can design.